So in this video, I'm gonna explain and draw for you the proof of theorem 1.10. Theorem 1.10 actually is two theorems. It's theorem 1.8 is the backwards direction, theorem 1.9 is the forward direction, and we'll treat these separately. What does it say, this theorem? If we have a graph that's sufficiently large, meaning at least 3 vertices, then the graph being connected is equivalent to saying that there are 2 vertices in the graph, u and v, such that no matter which one of the two I delete from the graph, the resulting graph is still connected. There's a few remarks I want to make here that are important, right? So the first thing here is this statement. G contains 2 vertices u and v. These 2 vertices u and v, these names are just made up in the statement right here on the spot. These are not names of vertices given by the graph or anything like that. These are sort of fake names. So if I have any graph, right, like I have a graph and it has a vertex set and an edge set, and you would have a vertex set which is maybe I don't know, v1, v2, all the way up to vn. This u and this v could be any of these 2 vertices. So these are placeholders for this. And this is very, very important to understand. This is like something that's done casually a lot and all over graph theory, that you just name the pieces of the graph as you go along, and you may give the same name, or you give the other way around. You give different names to the same vertex at several different steps of the proof. You want to avoid giving the same name to the 2 different vertices, but the other way around is completely common. So try not to be confused by any of this. This is very important in many graphs, that you can sort of just make up these vertex names or edge names as you go. So let's clear this up. And let's start with the backwards direction. And let's draw a picture. So we want to show that if there are 2 vertices, that removing them from the graph separately leaves connected a connector graph, then the graph itself had to be connected. So let's draw a potato for our graph. This is G. And let's have a vertex in here. Let's call it U. And another vertex in here, let's call it V. And if I cut away U, what is left is this whole graph here. So this is G minus U. And if I cut away V like that, what's left is this rest of the graph. Let's say this is G minus V. And what we want to show is that the whole graph G is connected. So that means between any 2 vertices of the graph that I pick, I can find a path. So I would like to choose 2 vertices, x and y maybe, give them 2 different names than the u and v that we have already. And I want to find a path between x and y. Now the question is, which are x and y, right? X and y could be in the middle part of the graph, which is neither u and v, or one of x could be u, or one of x and y could be v, or both of them could be u and v. So let's start with the cases. So if neither x nor y are u and v, and we want to find a path between x and y, what can we do? Well, both of x and y lie in G minus V, so there exists a path between the 2 in the red graph, the one that doesn't contain V. So, and we're done, because we found the path, because this path also exists in the big graph G. So that's the first case. The second case, well, if this x here actually is U, right? We can make the same argument. We just look at the path that exists in x minus v, in g minus v, and this is our path in g. So that's our first case. That's sort of the same thing as the first case that we had. Now, let's see what happens if, as the third case, one of them is v. Well, if one of them is v, the other one is somewhere else, maybe not u, then what we can do is we look at the green graph and find a path in the green graph, because neither of these is u, so there's a green path between the two. Okay, that works. So the only remaining case is that one of them is u and the other one is v of x and y. And now we want to find a path from u to v. That's the only remaining path that's needed, that's not implied by the conditions of the theorem. And how do we find that? Well, we can't just use the red graph, and we can't just use the green graph, because one of the vertices is missing in the red graph and the other one is missing in the green graph. So what do? Well, we just look at another vertex that we know that exists. Let's call it w, which is a vertex, a third vertex of the graph. This is the condition that we started with. The graph has at least 3 vertices. So we need this condition for this step of the proof, that we have at least 3 vertices, so we can pick it up. And now we can do a green path from w to y in the green graph, and we can do a red path from w to x in the red graph, not going through v. So, and then putting these two together, we get a walk from u to v. And this walk, so this walk may see some vertices twice, but this walk contains a walk by just cutting off those loops that we see here. And this is our path from u to v that's missing. So let's check that we covered all our bases. X and y could either be, neither of them could be u or v. We covered that case. It could be one of them is u and the other one is not v. We covered that case. It could be one of them is v and the other one is not u. We covered that. And this last case, one is u and one is v, is covered just here. So that was the backwards direction. Next, the forward direction. So for this direction, we use the concept of the diameter. So we will pick u and v such that the distance between u and v is the diameter of our graph. And this is well defined because our graph is connected. What is the diameter? It's the largest of those. So this diameter is greater or equal than the distance between x and y for any 2 vertices x and y. Okay, so this is how we pick our 2 vertices u and v. And the claim is this is all we need to do. And why is that the case? Well, again, we have our graph G, and we have a vertex u and a vertex v, so that the shortest path between the two, which is the distance, is the longest amongst all pairs of vertices. So why is our graph now connected? Our 2 graphs, why are they now connected? Well, let's again cut away the vertex u and look at this green graph and see that it's connected. And the red graph, we don't really have to do because the argument is just going to be the same as the one for the green graph. So let's look at 2 vertices in this graph, x and y. And what can we say about these two? Well, the distance between x and v is at most the distance between u and v. So if I take any path from x to V in the blue graph, any shortest path that I take, it cannot contain the vertex u. Why can it not contain the vertex u? Well, I need to make at least one step to get from x to u. And then the shortest path that I could attach to that to get to v is the length of d of u and v. But there's a shorter path than this path, which is one longer, at least one longer than the path from u to v. So that means that this blue path does not contain u, therefore it lies completely in the green graph. And similarly, there's a path from y to v. Y could be v itself, then it would be a path of length 0. But there is a path from y to v. The shortest path from y to v does not contain u. And now this again means that x and y, there's a walk from x to y going through v. So therefore, by the theorem that we had before, there's also a path that goes from x to y. How do we get that path? Well, we just walk from x along this path until we intersect the first time, possibly in v, the path from y to v, and then we just proceed on that path to get to y, and that will be a path. So that's the other direction of the proof, and we are done, because again, the argument for cutting off v here is exactly the same.